Ready to unlock the mysteries of quantum bonding? Today, we'll connect the dots between the antisymmetric state, molecular orbitals, and electron-proton potential energy. Here is a diagram of the hydrogen molecule, H2, showing the distances between each pair, with the protons plus E, the electrons minus E, and all their respective distances. Clearly, trying to find a Hamiltonian for this system is not going to be easy, so we break it down into parts and approximation schemes. And part of that leads us to today's problems, which is problem 8.12 and 8.13, in which we want to show that the antisymmetric state, equation 8.56, can be expressed in terms of molecular orbitals of section 8.3. Specifically, by placing one electron in a bonding orbital, equation 8.38, and one in an antibonding orbital, equation 8.53. And for problem 8.13, we want to verify equation 8.63 for the electron-proton potential energy, which requires that we use the antisymmetric state. So, why do we care? Well, the antisymmetric state keeps popping up. And remember, back in chapter 5 when we looked at the interaction of particles, electrons have to be antisymmetric under interchange. So if we maneuver them, we have to put a minus sign, and that's what the antisymmetric state tells us. This brings into a whole host of quantum statistics, whether it's Fermi-Dirac or Bose-Einstein. We have to utilize the statistics in large systems because we can't find a Hamiltonian that can account for every single interaction pair in these large molecules. We already see how complex it was for hydrogen, yet alone trying to put together everything in the classic three-body problem for the ion or even larger systems. So, that's why we have to use statistics. And then from that, we understand that the wave function symmetry allows us certain key advantages or disadvantages, so that helps us. The bonding and antibonding orbitals will be discussed too, but again, that takes into account the antisymmetric state and symmetries that we have. And then, of course, we care about the electron-proton potential energy because this gives us a nice approximation scheme to seeing how more complex systems happen. That being said, the challenge is that this is slightly abstract in nature and its computational demands are heavy. Especially if you want to program any kind of graphical result, you're going to have to know how to maneuver this in computational worlds, which is not exactly easy at first sight. And then, of course, you're stuck trying to interpret the results of this. So, that being said, the challenge that I would like to issue is what is a big approximation scheme for the H2 molecule that is talked about often in quantum chemistry? That being said, this is pretty straightforward, all things considered, since we're just verifying and showcasing that one form is equal to another. But you can still have the PDF for your collection. All you have to do is access it using the link below, and you'll be good to go. If you find value in this content, you can make a big difference by liking, subscribing, sharing it with a friend, or donating through Buy Me a Coffee. No account required. Your support means the world to me and helps keeps this journey going, especially when we get busy this fall. So with that, let's get busy in this question. All right. So stop number one, we are going to focus on problem 8.12, which is to show that the antisymmetric state, which is composed of the bonding and antibonding orbitals, is also antisymmetric. So let's write this in a more elucidating way. If we're given equation 8.56, and the minus sign tells us that we're the antisymmetric, so we have a minus sign between the two superpositions, we're good to go. And the normalization factor has the minus to verify that as well. So if we look here, we can write this as psi naught, again, some type of hydrogenic orbital with the distance r1, and then same thing but with r2. The prime coordinates go for proton 2 to electron 2, something like that. We saw that in the picture beforehand. Primes are from one proton. The unprimes are from another proton, so that's why we have it here. Then this would be to electron 1, electron 2, proton 2 to electron 1, proton 2 to electron 2, and so that's what we have here. but we can rewrite this in a little more elucidating way, because we can write that this is for psi b with the vector r1, and then psi b vector r2, so proton 1, proton 2, electron 2, electron 2. Same thing here, psi a, so electron 1 for proton 2, electron 1 for proton 1, and we're good to go. That being said, if we want to introduce the bonding and antibonding orbitals, then we can call upon equation 8.53 and 8.38. And here 8.38 is the bonding, where we have a plus sign in between, and psi a is the antibonding, where we have a negative. And of course, if we plug them in all their jurisdictions and all their right places, of course, color coding to match that, we see that we can factor out all the a's, so we get some new normalization factor. This is not really new, not really crazy, but here we see that we're going to have to go ahead and distribute this curly bracket into that one, and then the minus sign of curly bracket into that one. And from there, we'll see how this simplifies. And we remember, we're trying to show that this is equal to another antisymmetric state. So we need to look for the form where they have a minus sign, and we'll see how that simplifies next. Okay, so after combining all the normalization factors into one, big A, whatever you want to call it, we see that after distribution, we get a whole collection of the psi naughts with the respective r's as their arguments. And in doing so, we see that we get psi naught r1, psi naught r2, but then with the minus sign on the other side of the bracket, we get a minus psi naught r1 and a minus psi naught r2, so that cancels with that. Again, the color coordination doesn't really matter here so long as we have the same argument style. So hydrogenic orbital at r1, hydrogenic orbital at r1, r2, r2, cancel, cancel, and we're good to go. Similarly, on the back end of the distribution on both sides, we have psi naught r1 prime and psi naught r2 prime. Psi naught r1 prime, psi naught r2 prime, cancel, cancel. And again, the minus sign from the distribution, double minus, so we're good to go. And now we can see that once we cancel these out, we get a collection here of hydrogenic orbitals at different radii. So as we see, we'll go ahead and change the color scheme. This goes to the top line here, and these two go to the bottom line here. And we see that we get hydrogenic orbitals matching at the same locations. So that's what we're going to have to simplify now. So we get a minus minus, that gives us a -2. Then we have a plus plus, that gives us a +2, all at R1, R2 prime, R1 prime, R2 prime. So if we factor out this -2, we can put that on the normalization and create a new normalization factor. Cool enough. And then we're left with psi naught R1, psi naught R2 prime, minus psi naught R1 prime, psi naught R2, which is exactly the antisymmetric state that we were looking for. R1, R1, R2 prime, R2 prime, minus sign right in the middle, R1 prime, R1 prime, R2, R2. And we get the same form. Remember, we saw these happening back in chapter 2 when we were saying that any two solutions to the Schrodinger equation that satisfy all the conditions, orthonormal, complete, yada, 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 they also form a new solution, and all we had to do was verify the forms matched, and through appropriate cancellations, they did. So this should be not surprising, but actually something that we should expect. And we see that we keep building self-consistency in the theory because of that fact. So that's pretty cool. But with that, we conclude problem 8.12, and now we can utilize this result in the next problem. Let's see how we do that. This brings us to stop number 2, where we need to find the expectation value of this, where this is the electron-proton potential energy from the Coulombic potential that we see here. So let's rewrite this with the appropriate wave functions and not just keep it in the curly brackets, but actually showcase what we're trying to do here. And in doing so, we see that we get equation 8.63, which is the expectation value. But we know that the expectation value has to be sandwiched between two wave functions, so the inner product. And that's where we call upon psi plus or minus. And now the psi plus or minus is coming from equations 8.55 and 8.56, which is the symmetric and antisymmetric states. Okay, so if we can show that it works for both of these, just keeping track of the plus or minus signs, which is not that easy necessarily, but a must-have in order to simplify, then we're pretty good to go. And so we go ahead and multiply this by a 1, which we'll put to an a over a, so that we can utilize what we saw last section with the direct integral, the exchange integral, and the overlap integral. So we'll see that come into play relatively soon. Now, this normalization factor that we saw, well, we had an a plus and an a minus for the symmetric and antisymmetric states. That comes from equation 8.60. So we'll plug that in later, but because it is just a constant, we can bring it outside the Dirac notation and the inner product, and we're good to go. So we see that here. We replace this R1 with the A, and then we leave an A over R1. And again, we just put the A's in there so where we can actually make the substitution with the previous notation of all the different integrals. So the I, D, and X notation that we had saw last section. So we're good to go. Now, what we're stuck with doing is to distribute this argument with both of those and this argument with both of those. So we're going to end up with 4 inner products. And let's see what those are. First, so this one. And then we have this one and this one, so the plus or minus comes outside. Then we have the second with the first one, so plus or minus on the outside, and the second with the second. And here's where we have to be careful, because if we multiply, this comes from the fact that we have a plus minus multiplying a plus minus, and a plus always lead to a plus. And a minus times a minus always leads to a plus, so we just simplify down to 1 plus sign. That's the idea there. That's why we don't have a plus or minus on the last term. And now we see that again, linearity can come and help us, because if we look at this in the terms of integrals, we can note very quickly that R2 prime, for example, here in the first distribution, we said R2 and R2 prime don't have anything to do with R1, so we can separate out those integrals into an R1 integral and an R2 prime integral, and then we can simplify them down. So that's what we'll do in the next step, and then it will simplify very quickly to what we expect. Alright, so a little bit small here, but now we've done and we've compiled all the arguments that are relevant to one another over here, all the arguments that are relevant to the other argument over here, and we do that for every single pairing. And now we're in a situation where we can make an actual substitution on these things and actually go ahead and push forward. So first, what we observe here is that equation 8.40, this gives us what we call the overlap integral, which is because it's R2 and R2 prime. So whatever argument and its prime is the overlap. Here, in the first part, we see that evaluating this turned into a 1, which we see here. This is just the normalization between two common factors. So we're supposed to be normalized, so that works. Same thing happens here. We get a normalization. That's right there. And the rest, we have to plug in some kind of substitution. So for what this arrow is pointing to happens right here. Notice that it's R2 and R2 prime. That is the overlap integral. So we put an I there for it. So we have an I here. Notice that we have one that looks like it right here too. So we have another I. And then right here, what we see is that for R1 prime, we have equation 8.47, which tells us that this is the exchange integral. And so we have one right here. So that puts an X right there. But also we have an R1 prime, R1. Again, we get another exchange integral. So we're taken care of there. And then lastly, our direct integral has the primes with the expectation value of an R without the prime. So we get all the substitutions we need, and we're good to go. Now, again, these aren't necessarily that easy to see firsthand, so I just go ahead and list out all the equations in the PDF. Feel free to grab that so we can actually go back into simplifying. And then we see that the a squared up front here we can actually plug in, again, thanks to equation 8.60, and we see that we get another factor of the overlap integral that we see, and now we just simplify down. The square undoes the square root, so you're left with a 2 times I plus or minus, or 1 plus or minus I squared. Then we see that we get 2x times I integrals here, so that just leaves us with the 2 right there. D times 1 gives us D, and then we have 1 times 1 gives us 1. So we're all good to go. And thus, we verify, as the problem wanted, that we get equation 8.63 in the form that they wanted. So the 2 that was in the denominator here and the negative sign get put out front. Then, of course, we see our friend E squared over 4 pi epsilon naught over A. So, again, that's been common for quite a while, since chapter 4. And then we see some combination here of all the different overlap, exchange, and direct integrals. So that brings us to our conclusion for 8.13. So a whole lot moving on, but nothing too rigorous in this problem. I think the hard part's going to come in and trying to make any kind of conceptual understanding from this while it's still a little abstract. Although we were actually able to find a kind of closed form solution for the energies of this particular molecule. So that's kind of cool. And again, the approximation method that they use has a very specific name, so be on the lookout for that. All right. So, in summary, well, we got to show the antisymmetric state and its application to the energy approximation, so that's pretty cool. It wasn't really too bad in my opinion. It was just your note keeping had to be on par, and again, the PDF will have that for you if you want it. Everything was pretty much laid out in the video, so you're not missing much. That being said, you know, going back to the interaction of particles in chapter 5, a relatively brief chapter, all things considered, that's probably going to be the nuance of moving forward in a theory, because isolating systems is one thing. The measurement that we saw in chapter 7 on just a hydrogen atom and all the correction factors was, mesmerizing to say the least. But we see that bigger systems need better approximations, and that's what we're gearing to do now in the rest of the book. So be aware, interactive particles is definitely going to lead to something, and that's why, thermal physics and quantum mechanics mixed together in StatMech, and that's what drives people crazy. I mean, we've heard of path integrals and all these other fun things. That's very difficult to comprehend, and there's a large number of particles bouncing around doing crazy stuff. So being able to broaden our scope is what's going to happen next. And that's going to be a very fun challenge. That being said, I need to give a massive thank you to all my supporters for making this possible. I'm extremely grateful for your support. And if you'd like more, you can also become a patron for access to supplemental material, especially as we broaden our horizon. And by becoming a patron for access to the supplemental material, current and future projects, and one-on-one help. New content is posted weekly to help fuel your curiosity, which is only going to get more and more. We are stuck with more questions than we are answers, so it's going to get more intense here soon. Books, notes, and other reference materials are found below. If you have any questions, please feel free to reach out. But with that, as always, thank you for watching, and until next time, stay curious.